Sample problem number 6. This is yet another force of friction problem, but this one has a key difference. This one demonstrates the fact that the normal force doesn't always equal to the force of gravity. So let's see what's going on. A race car has a driving force of 11,500 newtons. Basically, this is the force produced by the engine and is delivered to the wheels through the drive chain, and the force of friction on the road is what actually causes the car to accelerate in the forward direction. As a result of the aerodynamic shape, the wind produces an additional downforce of 800 newtons. What are we talking about here? Well, we're actually talking about these objects here on race cars. Now, this is F1, which stands for Formula One style racing vehicle. And we have a couple of things that you'll see, some design features. Here at the front, we have what looks to be basically kind of a shovel. It's a scoop, but it's a scoop designed to grab air. At the back of the vehicle, there is something similar, but we call this a spoiler. These are intentionally designed to deflect the wind. And the idea is this. So let's say this blue vector represents the wind. The wind gets deflected up, but because of Newton's third law, since the scoop deflects the wind up, the wind pushes the vehicle down. So we end up getting a downward force on the front of the vehicle. That downward force means that the ground is now forced to put even more upward force to compensate. At the back of the vehicle, something very similar happens. The wind gets deflected up like this, and because of Newton's third law, every action has an equal and opposite reaction. The spoiler deflects the wind up, the wind pushes the spoiler and the back of the vehicle down. What this means is that in terms of the forces acting on the vehicle itself, not only does it have its weight, but we have a vertical component of this deflection going down at the front and at the back, which means that we have collectively, I should say, an increase in the down forces acting on the vehicle. And because there are so many more forces acting down, that means the normal force has to compensate and apply an even greater force acting up. So now in our given section, here's what we have set up. The problem is the letter D. I want to use D for the drive, but it makes more sense to use this capital D for the downward force thanks to the wind scoop and spoiler. So I'm using R for a race car. We could have used FE for the force of the engine, but this is the force of the race car. It's going in the forward direction, and the downward force from those design features of the vehicle are, of course, going down. Now, it does mention that the drag coefficient, and this drag coefficient is a combination of rolling resistance and wind resistance and all that stuff. Let's say it's 0.17, and the mass of the vehicle is 800 kilograms. So here's the key thing. In the y-axis, we have the normal force, the force of gravity, plus this additional downward force. Because of this additional downward force, the normal force is going to be bigger than, forgive the pun, normal. Normally, the normal force, that sounds really weird, I know. Usually, that's maybe a bit better, the normal force is going to be equivalent to the force of gravity. But as you can see, the magnitude of gravity is actually smaller than the normal force, and that's because the normal force has to fight against both the gravity and this downward force. The main question is, why do you want this extra downward force? Well, we'll see momentarily. The whole idea about what generates this FR, this force of the race car or the engine, is limited by the grip of the tires. The grip on the tires is going to be related to the force of static friction, which is equal to mu static times Fn. So in order to be able to accelerate as quickly as possible, this static friction has to be big enough to handle the demands of the engine. That means we need to have a large normal force in order to generate enough traction for the vehicle to accelerate. Now, there are two ways to increase the normal force. One, we can increase the mass, but the problem with increasing the mass is this. So if we increase the mass, then when we do F net equals ma, well, the problem is the acceleration gets smaller when we increase the mass. So we kind of have a dilemma here. We want the car to be as light as possible to be able to accelerate as quickly as possible, but we also want more grip. They work against each other. more grip requires more mass, but more mass ruins the acceleration. So this is how clever automobile designers are. They found a way to increase the normal force without having to increase the mass. So instead of increasing the mass, they added that downward force, which caused the normal force to get larger without having to add more mass. This gives us more grip, but keeps the vehicle light. And that's why they're designed that way. All right, so let's talk about solving for the acceleration of the vehicle. Well, we know the acceleration is happening along the x-axis because the acceleration on the y is going to be 0. It's not floating or sinking. Therefore, F net x is equal to the force of the race car plus the force of friction. These vectors are collinear, so I can replace F net with ma. And again, the reason why we can use ma is because the y component cancels out. The force of the race car is in the positive direction, and the combined force of frictions of drag is in the negative direction. But we know that the force of friction is equal to mu Fn. So I'm replacing my force of friction with mu times Fn. The issue, though, is that the most common mistake is thinking that Fn equals mg. In the previous examples, it was equal to mg, but not in this example. So in order to get this Fn, we have to go to the y component. Now, when we look at F net y is equal to the normal force plus the force of gravity plus this downward force. Dropping the vector notation, we get F net, which equals 0 because it's not floating or sinking. Normal force is positive, the weight or force of gravity is negative, and the downward force is also negative. Isolating for Fn, we have to bring these two terms to the left-hand side, which makes them positive. And again, Fg and Fd at this point are just magnitudes because we've already put the directions here. So the magnitude of Fn is equal to the magnitude of Fg plus the magnitude of Fd. However, we know that Fg is equal to mg, so therefore Fn is equal to mg plus Fd. And this is our equation number 2. So now we can sub in, actually doing that down here. Now we can sub in for our Fn over here. So what I have is A is equal to Fr minus mu Fn over m. I called that my equation 1. And now we're going to substitute this equation 2 into our equation 1 down here. So we're going to be replacing the Fn, but this is mission critical. You can't forget the brackets here. Otherwise, bad things will happen to you academically. So this is going to be mu times bracket mg plus Fd. This combined is the normal force. When we substitute in, we end up getting a positive maximum acceleration of 12.54 meters per second squared. So therefore, the race car accelerates at 12.54 meters per second squared in the forward direction.